So this part, I'm going to, it's going to deal with actual training of, if we have the time, 2 data sets. One data set, as you can see, is found here. Okay. All right. So the fundamental reinforced concrete structures training and test. So what I'm going to show you is the algorithm that was developed in order to train through the use of those 5 machine learning and artificial intelligence methodologies that I've shown you. Now, this is a data set that consists of fundamental periods that they were calculated through the approach of 3D detailed modeling. And as you can see, we just have the data set where we have the columns, and each and every column consists of an input. At the very end, we have the output. So let me close this. I wanted to show you, first of all, the publication in order to understand the physical problem, right? This was published at the Soil Dynamics and Earthquake Engineering Journal. So in this case, we use hybrid modeling and model analysis. We developed numerous models. Initially, we fixed them at the base, and these are using the 3D detail modeling and the hybrid approach. As you can see in this case, the beams and columns, part of them are modeled through the beam column flexibility based element, and the rest of the structure is discretized through hexahedral elements and embedded rebars, and that they can take into consideration yielding, rupture, and of course the concrete can take into consideration crack opening and closing of cracks, micro cracking, and so on. We investigated different fundamental period equations from international and national design codes, and of course you can see some of the modes that resulted from the numerical analysis, which we used in order to develop a 790 data sample data set. So in this case, of course, the software was validated through numerous experimental results that has the ability to capture the fundamental period of, in this case, reinforced concrete structures with and without shear walls. And of course, a structure which is entirely made out of shear walls. So these are some of the models with and without infill shear walls. These also the models with soil and the discretization of the soil where we take into consideration soil structure interaction. And of course, you see some results. As you can see, it's a highly complicated mechanical problem. And eventually we created the data set. And this data set now, I'm going to copy it into this folder here. I'm going to open it, and given the fact that our polyreg heat method, the polynomial regression method, has the ability to also result an equation, I will take this first row and say the soil depth of the soil domain, I'm going to name it, let's say D. The Young modulus of elasticity of soil, I will name it ES. The height of the building, which is an input that we require, is H in meters. The length of the building L, the width of the building B of the plan view, right? And of course, rho, we need to make sure that here we use Latin characters, and the period T in seconds. And now I'm just going to click save. I'm saving this, and also I'm copying the tree, right? The location of my folder. I start my Visual Studio Code where I come to the main Pi page, right? The Pi file. I paste, in this case, the tree, right? The root. And of course, I add here 2 slashes in order to make sure that it will be able to read it. And at the end, I need to as well, I click Control Save in order to save it. And now the only thing that I need to do is to run this by selecting it, these lines, and Shift Enter in order to execute it. As you will be able to see here, this was executed properly. And of course, now I need to import the libraries. And after importing the libraries, I will be able to open the dataset for the first time and split into train and testing. And here the test will be 30% and the training will be 70% of the dataset, which has 790 data samples. So this was done. We've read also, excuse me, the dataset and separated. And here we have the part where we are going to check for any missing values, any rows that they are exactly the same, identical. And if not, we will just get the information down here, which will say we did not find any, in this case, similar values, right? So as you can see, okay, so let me see that everything is fine. Now, if I run everything in a single shot, I have the ability to do that as well. All right, great. So as you can see here, number of missing values 0. And we have 6, as we've seen, we had input columns, and the last one was the output column. And of course, now we are ready to perform and execute the next commands, which is the descriptive statistics. Now, if I come back to my folder, this folder 1, you will see here I have a folder generated automatically, which is called predict, which is in this case doesn't have anything. Then ML models, here I will get my results in terms of graphs and Excel files. And of course, the descriptive statistics, where I will get my CDF curves, trees, and different, in this case, graphs that will help me better understand the nature of my dataset. So after executing these lines of code, this is going to finalize. And then if I come back, I will be able to see that I have an executable file, an Excel file, excuse me, which is created. And now I should see as well the different graphs. So let me change this. Let's see, first of all, the Excel file that was created. So my data set, as we said before, had the depth of soil, the young modulus of soil, of the soil domain, and the height of the building, the length and the width of the building. And of course, the ratio of shear walls. What is the percentage of shear walls along the direction that you're planning to calculate the fundamental period versus the area of all sections at the ground floor? So as you can see, we have mean, median, standard deviation, minimum and maximum value for each and every input feature, and skewness and kurtosis. So closing that, automatically the algorithm generates an all-by-all correlation matrix. And as you can see, this is of course ready to be used for a publication that you might work on. And here, all right, let me see if I can, okay, rotate this. Here we can see, in this case, the features versus target, and we see the distribution. As we can see, in this case, we have the percentage correlation for rho, width B, length L, right? And if I make this a bit bigger, you can see here, these are multiple graphs in a single PNG file, and the distribution can be seen. This is the convergence history, and of course, the distance versus similarity. And this is the map PNG of each and every feature found within our dataset. Now, let me go back and continue with the next step, which is the machine learning part. Now we are ready to train our models. So if I select the linear regression, which is the simplest and should be the worst one out of all of them, I select, I run, and as you can see, this is already done. Okay. So if I come back to the folder, enter the ML models, and go into the linear regression, right? This is ANNBN, artificial neural networks by neighborhood, deep artificial neural network, linear regression, non-linear regression, which is our polyreg, right? This is random forest with high parameter tuning, and this is the XGBoost with high parameter tuning and cross-validation. So if I enter here, I will be able to see my first results. Also, I can see here that the correlation parameter factor for the training data set was 0.99 and for testing 0.99, which means that it gave us a very good correlation factor, but the mean average error, absolute error, is 13% on the training data set and 15% on the testing. So if I come here and open, in this case, this figure, I will be able to see on the testing set the performance of my predictive model that resulted from the linear regression. And of course, in this case, I will be able to also see the one over here. Where is it? Should have gone back, or no, this one for the train, right? So this is for the train, as we can see. So linear regression prediction versus the numerically computed results. And of course, we are able here to see the error metrics, like the error on the test that resulted. And of course, our PDF, right, and CDF graphs, which are all automatically generated, ready to be used. So this is extremely easy. And of course, this is not just done for the linear regression, but for all the methodologies. Again, we have here a text file with the equation, which if I take this equation that was generated, and it's specifically generated to be used directly within our data set, if I take and open my Excel, the same thing applies, of course, for the polynomial regression. So the linear regression and the polynomial regression are both methods that actually allow us and provide us they derive an actual equation that can be used directly in your Excel. So as you can see, the actual prediction is 0.218 seconds, and the actual value is 0.198, which is very close. And if I copy paste the whole thing, then as you can see, the values are similar. And we know that the MAPE is 13%, right? So I'm deleting this. I will not save it because I don't need to save that. Now, the polynomial regression requires the definition of rounds, right? And in this case, as we can see, the number of rounds is 1,000, and the degree of the polynomial is to the power of 3. So if I come here and run this, Shift Enter, I will see now, you see this is the round. We are already at 100, 200. I just have a simple computer, right? A simple laptop, nothing significant. And Python is not the fastest language out there, that's for sure. So it's doing its magic in an automatic manner. And of course, now it's done. The sensitivity curves are out, care for features for each and every feature. And as you can see, this MAPE is 5% on the training data set and 6%, just 6% on the testing, and almost absolute perfection in terms of correlation factor. So if I go back to my ML models and go in the nonlinear regression, I will be able to see here the text file of the equation for the Excel file, the formula also given by using H, B, and L, and rho, right? There is rho. Or I can get, again, the equation, copy paste it from here into my Excel and directly get my results. On top of that, in an automated manner, we have the development here of the convergence, and we can see a very nice convergence. These are very important graphs that we need to excuse me, see and have in order to know that our model was not like a random local minimum, right? And of course, the mean average error according to the training, this is the target versus predicted results on the test data set, and this is the one on the train set. Now, of course, we have the sensitivity analysis, which is also extremely important. And the sensitivity analysis tells us if, let's say, the width, as you can see here, is an important input feature. So as you can see here, the width does change the fundamental period, and it affects the fundamental period. And the depth of the soil, not as much. So it's not a very important feature. Here we have the Young modulus of the soil, but we only had two numbers when we created this data set. We used significantly more when we performed the analysis on the steel structures with the high performance computer. Here we didn't have a high performance computer, so we couldn't use many values for the Young modulus of the soil. This is the height. As we can see, the sensitivity of the height of the building, it is very significant. And this, of course, is the length, which is also significant, but not as much as the height. And this is the rho and the effect of the shear walls on the corresponding mechanical response, let's say, and the calculation of the fundamental period. Now, if I come in the ML models, in the ML models folder, I will be able to see the mean average error of the two machine learning algorithms that I used thus far, the nonlinear regression and the linear regression. Now, if I close this and go back and execute my XGBoost, by the way, the recommended value for the threshold of minimum tune rounds is 100. I'm going to use just 15 here in order to save up time, given the fact that this can be time consuming. So as you can see, we already executed 3 rounds. The threshold stop is 10 to the minus 2. So 4 rounds. And let's say now I say, oh my God, I don't have time. So what can I do? I can, like at the 6th round, click Control C and abort it through keyboard, and automatically the algorithm stops the training. It finds the best model, predictive model, out of those 6, only 6 rounds, right? And look at that. For only those 6 rounds, the training error was just 2%, and the test, of course, was 8 because I didn't even allow it to perform 10 rounds. So this actually shows the efficiency of the XGBoost, the proposed algorithm with hyperparameter tuning and cross-validation. And now if I come back here and open this figure, right, as you will see, the XGBoost, which just performed only 6 rounds, derived an MIA, which is around here, right, which is less than 3%. This is definitely very interesting and extraordinary to have this type of tools, the efficiency that this will provide to any researcher that get their hands on, and especially our students have the privilege to use these automated tools and perform our research, and after they develop their data sets, of course. Now, here is the Excel file where all the results are shown in a concentrated manner for training and testing, linear regression, polyreg, and XGBoost, and of course, correlation factor, MAPE, MAMPE, MAE, and whatever you want there, you can, whatever you need, you can find it here in terms of error metrics, and of course, the duration to perform the training testing, and of course, in this case, as we can see, so far the XGBoost was the slowest, but 24, not the slowest, is exact opposite. It required the largest amount of computational time, but we also stopped it at the 6th round, right? And we can do the same thing for random forest. I just want to finish this. Okay. And again, given that we don't have sufficient time, I will stop the random forest as well. And then I will move to the next one, which is artificial neural networks by neighbors, right? which is way faster, and this works significantly well when the data sets are large. And of course, this is done, and as you were able to see, it finished quite fast. And of course, the deep learning, I just used 10 rounds, but I'm just going to allow it to run for a couple of rounds and then move to the next step, which is the sensitivity analysis. So this is round 1. You can see here the different parameters that are used in order to perform the tuning and perform the calculations. And therefore, this number here, usually the 400, is the one that controls if we have many calculations to perform or a few calculations. So definitely the fact that I'm using my personal computer isn't making things easy for us. But again, as you can see, the rounds are performed, and after I stopped it, you will be able to see the calculation and the development of the different output that, again, once more, are stored in this folder. So these are the artificial neural network by neighborhood done, the deep learning, which was just generated with different, in this case, figures, including, in this case, loss history percentage for the deep artificial neural network model, and linear, nonlinear, we've seen it, random forest, there are the results, and XGBoost. Don't forget, though, these are not optimal results, given the fact that I did not allow the algorithms to run for a sufficient time and get maximum, in this case, accuracy. And even though I got some really good results, right? So this is features importance graph based on XGBoost, height, length, ratio of shear walls, Young modulus of the soil, width of the building, and last, the less important one was the depth of the soil under the foundation. So these are extremely important figures and output that we now have under the fingertips. And of course, the MAET on the test set that resulted from all 6 ML and AI algorithms. Now one might say, okay, what's next? Now let us check, right? Let us check the performance of our predictive models when it comes validation out of sample results. So if I go in this folder here, which is called predict, and paste this data set, the Excel sheet, which has the results that we did not use in the procedure of training, nor in the procedure of testing, and this data set uses values that we haven't used before, right? These are out of sample values, and we added in the predict folder, which is found in this folder here, folder 1, that I created at the beginning, right? I will be able to perform a sensitivity analysis, by the way. In this case, if we perform it, it gathers all the results from the 6 methodologies, and in this case, is generating all sensitivity figures, related figures, right? So these are all sensitivity figures. Before we go to the prediction, I wanted to show you this. These are based on XGBoost, and this is the comparison of all 6 methods and the sensitivity for each and every input parameter. So you have everything gathered up. And of course, now if I go back to the prediction, I'm ready now to execute the code which will read the data set, the prediction data set, and then run all models except from polyreg, because the polyreg will have the actual model in that the equation, which we can copy paste into the data set. So each and every methodology now is executed, And all the predictions can be found in the predict folder. And of course, which is very, very, very convenient, the corresponding graphs which show the performance on the out of sample dataset. And as you can see, this is ANN by neighborhood. The deep learning, as you can see, the deep learning here has a better performance. The closer the points are to the diagonal, the better the prediction. And of course, our CDFs here derived directly from the algorithm. And in this case, if we go, let's say, in the XGBoost, we have for all of the methods, we have an Excel file with the predictions, right? If I open this, I will see all the predictions stored. And you will see now in the Excel, right, the predictions for low, medium, and high. And predictions XGBoost, which is the prediction of the actual model here in this, the predictive model in this column, first column. And of course, the error metrics, right? Very important. Error metrics within our Excel sheet. And what do I mean by that? Correlation, mean absolute error, MAMPE, mean average error, and of course, alpha, beta error metrics that describe the overall performance of the XGBoost in this case. And this is the polyreg is empty, and one might say, okay, how come? Because if I go to the ML models and I go to the nonlinear regression, the polyreg, I can get the equation here, copied, come back, open. Actually, I need to open the data set, which is the validation data set, right, for my predictions. You will see it now. And if I take that formula and paste it here, bop, there it is. You can see it's working perfectly fine. And then I can copy paste it and check and compare, right? And I can develop my graphs as well. 0.18, 0.2, 0.87, 0.85, 0.2, 0.21. As you can see, predictions are quite accurate, given the fact that we didn't even play with the degree or the rounds, right, in the polyreg case. So this is just single try shown to you in like 30 minutes, and working with 6 different machine learning and artificial intelligence methodologies that were developed for the needs of our research, and definitely a very, very powerful tool.